Pi is 4. Not a typo, not a joke, not bad mathematics. There are places where you can draw a circle, measure all around it, measure straight across it, divide one by the other and get exactly 4. There are places where you get 2. There are places where the answer depends on how big you drew the circle. The number you memorized in school, 3.14, is correct in exactly one situation. And that situation does not exist anywhere in the universe. Nobody told you that. Not because they were lying to you. Because the sentence that makes it true is so wise, so obvious sounding that it got left out of every classroom on earth. I'm going to show you 4 places where pi is something else entirely. And then I'm going to show you why that doesn't mean your teachers were wrong. It means something far, far stranger. Before we go, if you like the kind of question that quietly takes the floor out of from under you, subscribing genuinely helps the channel. What pi actually is. Here's the first thing to unlearn. Pi is not a number that exists somewhere carved into the universe waiting to be discovered. Pi is the answer to a question, and like every answer, it depends entirely on the question. The question is this: if I draw a circle, how many times does the distance across fit into the distance around? That's it. That is pi. Not a constant handed down from above. A measurement, a ratio, something you do. Take the circle, walk around the edge, note how far you walked. Now walk straight across through the middle. Note that too. Divide the first by the second. 3.14 every time. On every piece of paper, in every classroom, in every country on this planet. Which is why it stops feeling like a measurement and starts feeling like a law. But every measurement carries a hidden question with it. Not just what you measured, where you measured. And that is the sentence nobody says out loud. The basketball. So let's change where. Find a basketball, draw a dot on it. Now draw a circle around that dot. Every point exactly the same distance from it, measured along the surface, not through the ball, along it. Because you live on the surface, and the surface is your entire world. Now measure around the circle, and then across it, again along the surface, over the top, through the dot, down to the other side. Divide. You don't get 3.14, you get less. And you didn't measure wrong. Your ruler is just fine. Your circle is a perfect circle. The number is simply different. Here's why. On a flat page, when you double the distance from the center, the edge doubles too. Everything scales cleanly. That is what flat means. On a ball, it doesn't. As your circle grows, the surface curves away underneath it. The edge can't keep up. It runs out of room. The distance around grows slower than the distance across. So the ratio shrinks, and it keeps shrinking. The bigger the circle, the smaller pi gets. So push it to the limit. Put your dot on the north pole of the earth. Now draw the biggest circle you can. The equator. Every point on the equator is exactly the same distance from the pole. So yes, it's a circle, a real one. Measure around it. That's the full circumference of the planet. Measure across it. From the equator, up over the pole, down the other side. That's half the way around the planet. Divide one by the other. 2. Pi is 2. Exactly 2. No approximation, no rounding, no trick. And now flip it. Take a surface that curves the other way. A saddle, a bringer, the shape of a mountain pass. Now the surface opens outward faster than flat. There's more room at the edge than there should be. The circumference races ahead. Pi goes up 3.2, 3.65. As high as you want, if the curvature is strong enough. So already we don't have a constant, we have a range. Curved inward, less than 3.14. Flat, exactly 3.14. Curved outward, more. Which raises a question that should make you slightly uncomfortable. Which one are you standing on? Hold that thought. We're coming back to it, and it's worse than you think. Quick one. If this is landing, subscribing takes a second and genuinely helps. I appreciate it. Manhattan. Now I want to break it in a completely different way. Not by bending the surface, by changing what a distance means. Imagine a city built on a perfect grid. Streets running one way, avenues the other. Buildings filling every block. You're on foot. You can't walk through buildings. You can only follow the streets. So, you want to get to a point 3 blocks east and 4 blocks north. How far is that? On paper, with a ruler, it's 5. Straight line, a diagonal, done. But you can't walk the diagonal. There's a building there. You have to go 3 east and 4 north, or 4 north and 3 east, or zigzag. It doesn't matter which. It's always 7. In this city, the distance isn't 5, it's 7. And this isn't a game, it has a name. Taxicab geometry. And it gets used constantly. Routing software, chip design, where circuits can only run along axes. Whole branches of data analysis, where the question how different are these two things is measured exactly this way. It's a real, rigorous, internally consistent geometry. So, what is a circle in this city? A circle has one definition, and it's beautifully simple. All the points that are the same distance from the center. So stand at an intersection. Find every point that is exactly 10 blocks away. 10 blocks by walking, not by fly. 10 east, 10 north, 10 west, 10 south. All on the circle, but also 5 east and 5 north. That's 10 blocks too. And 6 east, 4 north, and 9 east, 1 north. Plot every single one of those points. And you don't get a round shape. You get a square. Standing on its corner, a diamond. That is a circle, not a metaphor for one. In this geometry, by the actual definition of the word, that shape is what a circle is. So let's do the only thing we have been doing all video. Measure around it, measure across it, divide. Across the middle, 20 blocks. 10 out to the edge, 10 back, round the edge. Each side runs from one tip to the next, 10 blocks across, 10 blocks up, 20 blocks per side, 4 sides, 80 blocks. 80 divided by 20, 4. Pi is 4, exactly 4. Not approximately, not if you round it. In a taxicab geometry, the ratio of a circle's circumference to its diameter is precisely 4 for every circle of every size. There it is, the number from the thumbnail. It's real, it's clean, and it's been sitting in mathematics textbooks for over a century. Space isn't flat. No, everything so far you could dismiss. The ball is a curved surface. The city is a made-up rule. Fine, you might say. Special cases out there in the real world, on real paper, in real space. Pi is 3.14. Here's the part that ruins it. In 1915, Einstein published the idea that mass bends space. Not space looks bent. Not it's a useful way to picture gravity. Space itself, the thing everything sits inside, is deformed by anything with mass in it. And we have measured this repeatedly. Light bends as it passes the sun by exactly the amount predicted. Clocks run slower near mass, which is why every GPS satellite carries a correction built in before launch. Or your phone would put you in the wrong town by dinner time. 2 black holes collided a billion light years away, and the ripple stretches and squeezes the space here on Earth by less than the width of a proton. And we felt it. Space is not a state. It's a fabric. It has a shape, and mass changes that shape. Which means the ground you're standing on right now is not flat space. The Earth is a lump of mass, and the space around it is curved inward, the same direction as the ball. So take a perfect circle, draw it out in space around the Earth, measure the distance around it, then measure the distance across it properly, physically, all the way through, the way a real ruler would have to go. The ratio is not 3.14159, it's less, only very slightly. The effect around a planet like ours is far too small for any ruler you own, but it is not zero. It's a real, calculable, non-zero difference. And go somewhere with serious mass, and it stops being subtle. Around a neutron star, the difference is significant. Around a black hole, it's dramatic. Draw a circle just outside the event horizon and measure across it, and you find the distance across is far bigger than 3.14 should allow. There is more space inside that circle than fits. The room in there stretches in a way flat geometry has no room for. So here's where we've ended up. 3.14159 is the ratio for a circle drawn in a perfectly flat space. And perfectly flat space does not exist. Not here, not on the moon, and not in the emptiest void between galaxies, where there is still faint curvature from everything around it. Nowhere in this universe is the condition met. 3.14 is the answer to a question about a place that isn't real. And yet, now I have to be honest with you, because this is the point where a lot of videos would stop, and stopping here would be a lie by omission. Pi is still 3.14159 exactly forever, and nothing I've said changes that. Here's how both things are true at once. There are two different questions hiding under the same word, and we have been letting them blur together on purpose, because that blur is the whole illusion. Question 1. In a perfectly flat plane, what is the ratio of a circle's circumference to its diameter? That question has exactly one answer, and it's not a measurement, it's a proof. You can derive it with pure logic, no rulers, no universe required. It would be the same answer in any universe, or in no universe at all. That's the mathematical constant, 3.14159, and onward forever, never repeating, never ending, locked, untouchable. Question 2. If I draw an actual circle in actual space with actual mass around it, and I go and measure it, what do I get? That's a physics question, and the answer depends entirely on where you are. On a sphere, less. On a saddle, more. In a grid city, 4. Near a black hole, 4 less. Here on Earth, almost exactly 3.14159, but not quite. Both answers are correct, and they're answers to different questions. The mathematical pi never changes. What changes is whether the universe you're measuring in matches the flat, idealized world that mathematical pi describes, and it never quite does. So your teachers weren't lying to you. They just left out 5 words that would have changed how you saw the whole thing. In a perfectly flat plane, that's the missing sentence. Every single time you were told pi is 3.14, there was an invisible clause attached, and nobody ever read it out loud. And once you notice that clause, you start seeing it everywhere. Parallel lines never meet in flat space. The angles of a triangle add up to 180 in flat space. The shortest path between 2 points is a straight line in flat space. Every one of those you were taught as a fact about reality. Every one of them is actually a fact about the model of reality. A beautiful, useful, staggeringly accurate model that happens to describe a place that doesn't exist. That's not a flaw in mathematics. That is what mathematics is. It builds perfect worlds, and it tells you exactly what's true inside them. What it cannot tell you is whether you're living in one, and you're not. You're living in a lumpy, warped, mass-riddled space where the rules are almost right. Almost. Close enough that for 3,000 years nobody noticed. Close enough that you can build bridges and land spacecraft and never once care about the difference. But not exactly. Never exactly. And there's something I find genuinely beautiful about that. The number is perfect, the universe isn't. And the tiny gap between the two is where all the interesting physics lives. So the next time someone tells you pi is 3.14, they're right. Just ask them where. If you want more of these, the question that looks settle until you lean on them, subscribe and you will see me in the next one. God bless you.